I don't know. I can try. Yeah. It might be plugged in. I don't see it. Is it that? So you also join Zoom call
Yeah.
and then share the slides. Okay. Start a few minutes late anyway. And we're still setting up and save stuff. We're waiting in a few minutes, but nothing's going on. Maybe mass, yeah. That room wasn't working for me. Yeah. Hey. You're securely not connected to the internet.
I think I might also not be on the waiting list.
So I can forward it to you directly.
Yes,
I'm gonna get a job for a while.
Well, mass or
if I manage to get it.
connect to the internet.
Otherwise,
I'm just coming from a warm place.
Yeah, it's strangely cold.
Connected, nice. Yep. With is fine, but then just mute.
Recording in progress.
Just turn your volume down. Yeah, okay, no, shit.
Hey, how are you doing?
Yeah. We do that?
Machine. Yes, okay, good, very nice. Yeah, no, we can-
Better now?
And then I think I'm gonna try that.
I think it's still.
I think you go, we can check, yes. Basically, it's still setting up the last, very last.
Now it should be okay. Okay, sharing. Yep. Okay, that looks right. Okay, and we can give Bruno another minute to get back to getting his jumper.
Sure, okay, but they don't go and reach for this. Yeah, but I want to go.
If it starts dying, you just have to talk fast.
Planning is actually putting the ISA model, so yes, if I could do it for the end model. Yeah. But the ISA model is more complicated. That's what I was so. Cool, and you said this is a typo? Yeah. That's a typo, it's the one under that is kind of related my some pressure. But cool, now we want it. Cool.
Weird moments.
We tried. We tried to pretend like it.
Exactly.
Pass them around.
Can we turn it up or the IC?
I don't know what it is. I don't know.
Is there like
I don't know if it's cold air or just the air recycling.
Yeah, also read up on your mic.
yeah, this is freezing cold.
Yes.
Ramon, can you? Okay, well, welcome everyone to this week's network seminar. This week we have Karel. Doesn't really need an introduction as he spent 4 years here doing his DPhil with Renault. And then he left for 2 years to do a postdoc in Leipzig at the Max Planck Institute for Mathematics and the Sciences. And now he's returned to do a brief postdoc again here in the Mathematical Institute. So he's going to tell us about some stuff he's been working on over the last few years. So Karel, please take it away.
Thank you, Tim. And in fact, I will give a talk that sort of segues from my talk 2.5 years ago that I gave here before leaving. So for those of you who are around. Yeah, so today I'll talk about some of the work I've been doing since I left here. And it's broadly speaking related to counting spanning trees in graphs. And I'll talk about some applications. One of them is discrete curvature, which of course I also worked on a lot. Yeah, okay. Okay, so let's jump right in with the basic object of study that we will think about today. So on the left here is a graph, which you probably know what that is. So a collection of vertices, as the black dots here, edges, which are connecting pairs of vertices, right? V and E for these. And then the main thing I'm interested related to these graphs are so-called spanning trees. I give a bunch of examples above here. And so in principle, so the definition of a spanning tree is that it's a maximal subset of edges, here a subset of edges, such that these contain no cycles, and they're maximal. So let's unpack what that means. So a maximal acyclic subset. Acyclic, well, you see from the pictures, none of these things here, these collection of subsets of edges have cycles. And maximal means that if I would try to add any further edge, I would create a cycle. So for instance, in the one here on the left, clearly there's no cycle, but if I would add this diagonal or this bottom edge, I would create a cycle. This is not allowed. So it means this is a maximal acyclic subset. Okay, so that's the spanning tree. Is that definition clear for everyone? And in general, just interrupt me. You can see I just have 16 slides and 50 minutes. So whenever you want to ask something, go ahead. So that's the basic thing I'm interested in today. And what will I do with them? Well, I'll be counting them, as the title mentioned. So I'll be counting spanning trees. This is something, a problem that's actually been solved in the 1850s. So what's new? I'll just give some sort of historical overview with different types of perspectives on this that can be generalized in different directions. Then in the second part, I will look at a sort of specific subproblem of this. Say I care about one of the edges in particular, maybe the edge in top. And then I'm interested to see how many of the total number of edges contain that edge. For instance, in this case, 5 of these spanning trees contain that edge. And that's what I'll call conditional counting. This will be related to the so-called effective resistance in a graph. And I'll give a new characterization result of what these fractions can look like. Okay. Then in the third part, I will use this new characterization theorem from the second part, and I'll apply that in the context of discrete curvature, which I will explain you what that is, and hopefully also what the result is. Okay, so throughout I will mention results that we're doing with Renault here, with Rafaela, I was a supervisor in Leipzig, and then Stefan and Andrea, who we had a joint paper, but I'll mention throughout which results are with which subset of people here. So is everything clear? So have a look at the definition. Okay, then let's start counting. Okay, so the setup, so the symbol of interest, right? What I'm interested in counting, I will write that as Z sub G. So if you know statistical physics, it's like a partition function in baby form. Okay, I will write summation over T, which just means this sums over all spanning trees. For now, this is just a number one. This will become a bit more interesting later. And this is precisely the number of spanning trees of my graph G. Okay, so that's the number we're trying to understand. Okay, and that's immediately the biggest spoiler. So this was solved in 1853, I think, by Christoph Kirchhoff. So you may know his name from some electrical circuit theory you've done in some course. And what did Kirchhoff prove? Well, he showed that this counting problem, while it's something sort of weird combinatorial, actually is solved by a simple determinant. So some simple algebraic computation. And in fact, it's equal to the number of spanning trees is equal to the determinant of something that's called a reduced Laplacian matrix. Instead of a definition, I will just give you an example. So say we have this graph that I showed you on the first slide. It has 4 vertices. I will associate to that a 4 by 4 matrix, where each of the vertices is corresponding to a row and a column. On the diagonal, I put a degree, so the number of neighbors. So for instance, vertex 2 here has 3 neighbors, so that's why there's a 3. And then off diagonal, there's a -1 if there's an edge. So for instance, 1 and 2 are connected. So I put a -1 here, 1 and 3 are not connected, so there's a 0. And this way you can fill in your matrix. You remove 1 row and column, you get a submatrix that's called the reduced Laplacian, and its determinant is equal to the number of spanning trees. Okay. And if you either don't believe me or get bored at some point, you can try and compute this and confirm that the 8 things I showed here on this slide are indeed all of the spanning trees.
It's equal to, what did you say that it's equal to?
This determinant,
Yeah.
the number of spanning trees.
Okay, yeah.
Yeah, so you should get 8 if you do this, and otherwise there's an error on the slide. Yeah.
So if you remove any row and any column, the determinant of this submatrix is the same.
Yes. And actually, if you remove like different rows and columns, you get a sign thing, but it's the same. Oh, this is part of the theory. Yeah. Okay. And it's actually, the proof is not so hard. It's some determinant identity and then interpreting smaller determinants in terms of trees or not. And the background is matrix theory. So this actually, the fact that this works is quite special. There's not many matrices or objects for which this works. So the specific setting would be regular matrices, objects you can count in this determinantal way. If you try to generalize it a bit more, this already breaks. So this is a very sort of miracle thing that happens. That's maybe why it was discovered so early. But I'll make a few pointers throughout, like how you can generalize things nonetheless.
Why do you choose that matrix?
This Laplacian matrix.
-1, yeah.
So here -1 is just because we're thinking about edge or no edge. Later I will introduce weights, and then this will become weights as well. And then you're counting with weights. And why this matrix? Well, because it solved the problem in a sense. So the original motivation for Kirchhoff, so he was interested in modeling electrical properties of electrical circuits. And this matrix governs a linear relation between potentials and currents in a graph, in an electrical circuit. So you say I measure voltages throughout my circuit. I want to know the currents. Well, you hit it with this matrix and you get your currents. So, and the reason behind that is, well, it's a Laplacian operator from Kirchhoff, exactly. Yes. So this, in the background, there's all of this motivation. Yeah. And then I think this sort of was post factum he found this algebraic identity. Yeah. Okay. Any questions? Good, thank you. Okay, the second way you could think about this counting problem is you make this fairly simple observation. It's called the so-called contraction deletion formula. It's a bit divide and conquer, right? So you say, I want to count the number of spanning trees of a big graph. And this is equal to counting number of spanning trees in two smaller graphs. Again, I will just give an example instead of defining them. So you take your graph, you label for a certain edge. In one of the subgraphs, you remove it. In the other one, you pinch the edge together. And now the number of spanning trees here is equal to the sum of all spanning trees in these ones. And these are smaller, so you sort of break up the problem and it becomes easier as you go on. Okay, and of course, in the background, this should be equivalent to the determinant formula. But this one is nice, for instance, if you want to prove some induction steps related to that number. Another reason to mention it is that this is something that you can see quite easily, but it is generalized in the so-called Tutt polynomials, an object that people care a lot about in algebraic combinatorics. So instead of just a number associated to your graph, this is a bivariate polynomial, so two variables, x and y. And if you choose special values for x and y, you get some numbers we already care about. So if you plug in 1, 1, you get number of spanning trees. If you plug in, I don't know, many other examples, but it sort of captures a lot of the algebraic structure of a graph in one single bivariate polynomial. And then the thing that relates Tutt polynomials to this formula is that this is, in a precise sense, the most general algebraic invariant that satisfies contraction deletion. So the moment someone discovers this and tries to push it to its logical conclusion, you end up with this bivariate polynomial from the early 20th century. Okay, so again, this is just to showcase that this number might seem simple, but it has a lot of nice generalizations. Okay, that's the second way of doing the counting. A third way could be, okay, what do I, and this is something I mentioned before. So what if you care about some related counting problems? So in this case, counting bases in a matrix. So just think of this as some generalization of counting spanning trees in the graph. Well, it was not known for a very long time, until 2018, whether this can be done even efficiently or not. And so for graphs, it just determines very efficient. But in this slightly more general setting, it was completely open whether or not that was possible. And it was settled in this sort of monumental series of papers. So this is the second paper out of a series of 4 very strong papers where it proved a lot of our conjectures as well. And they showed that you can do this counting approximately using some very sophisticated random walk on the space of all these bases of a matrix. Okay, so you have, as I mentioned, for us, our problem is very simple. It's just determined, but if you try to push it a bit further, it's still computable, but it gets to the boundary of what's not possible anymore. Yeah, and again, some very recent work, so these questions are still what people are actively researching. Okay, so as I promised, so we'll make it a bit more general or interesting. So let's now associate some variables to my edges. So every edge will get some variable associated, CD, and you can think of these as some real numbers, positive real numbers, but in general, they're just variables. And then for a spanning tree T, I will take this C to the power T to denote the product of all edge weights. So think of this as some weight of your tree. And now instead of just counting a number, I will define a polynomial. So I sum over all spanning trees of this monomial. And this is called the Kirchhoff. Let's see if we can draw a quick example. So say this is my graph. C1, C2, C3. So this one has 3 spanning trees. Then here ZG of C would be C1, C2 plus C2, C3 plus C1, C3. Okay, and you can see if you plug in 1 here, you will get 3, which is the number of spanning trees. Okay, so this generalizes the counting problem from the beginning. And as was asked before, if you have your Laplacian matrix, you can put these numbers in your matrix and get the same determinant of event. So this is a determinant of some matrix with weights. And it's called the Kirchhoff polynomial, of course, referring back to Kirchhoff. This is a very nice polynomial again, as you may expect. So it's multilinear, which means that every of these variables has degree at most 1. It's homogeneous of degree. Homogeneous means that each of these terms has the same degree, which is due to a fact that I forgot to mention, but let's go back. So here you see that each of these spanning trees has the same number of edges, 3 in this case, and this is true in general. So spanning tree will always have number of vertices minus number of components. In this case, 4 vertices, 1 component, so 3 edges. And this is true in general. And as a result, in this polynomial, each term will have the same degree, the same number of variables that you multiply. which is called a homogeneous polynomial. That's a nice property to have. And then second, and that's something that's much more surprising that you wouldn't guess actually, is that this polynomial has a so-called half-plane property. So if I will evaluate this polynomial by choosing some complex weights with positive real part, so I choose variables here, it turns out that this is never zero. What does it mean on the side of the Laplacian operator? That it's an invertible matrix, and that has everything to do with the fact that in this regime of parameters, so you should think of an electrical circuit where these variables are somehow impedances in your circuit. And Kirchhoff's current law tells you that you can always invert voltage to current, which means that your matrix cannot be singular, which means that the determinant cannot vanish. So this is, in polynomial language, physical property. And that's why actually people first even thought about looking at this. So that might seem okay, nice observation, but it turns out that this was a very nice property to ask for. And then people said, okay, what if we just ask from any homogeneous polynomial if it has this property? This turned out to be a very nice mathematical object, which down the line led to a theory of Lorentzian polynomials, which is partly what Junihao was awarded the Fields Medal, right? So this simple observation from physics, really down the line in very recent work, so this is last 5 years, comes to sort of a very nice object in algebraic combinatorics as well. Okay, so yet another example of how this simple question has a lot of generalities in its work. Okay.
So the half-plane property was published also in this paper?
No, this is due to Wagner, I think, in Canada, like 2004-ish, I think was the first papers on.
And does the half-plane property already implies Lorentzian?
But it's not equivalent. So I don't think every half-plane property.
Oh,
So
okay.
the class of Lorentzian polynomials was defined by Peter-Brennan and Junihao, and it contains this class. But it's sort of this, like Peter-Brennan worked a lot on this half-plane property and sort of generalizations of that, where instead of just thinking about the upper half-plane, you think about any half space and want your polynomial to vanish there. So it's sort of, this is one of the places where this theory that ended up with Lorentzian polynomials started. Yeah. So this is early 2000s, I think, was the first. Yeah. I mean, maybe specifically this observation is older for the Kirchhoff polynomial, but the theory of half-plane property polynomials, I think, started early 2000s. Yeah. Okay, but we won't talk much more about polynomials if you don't feel comfortable with that. So from now on, C will just be a positive real number. There are numbers again. Okay, and now I'll come to the second part, which is conditional counting. So as I mentioned, what I'm interested now in is to fix one specific label that I care about, and then counting the fraction of all spanning trees that contain that edge. So in this example, you can see that 5 out of 8 of my spanning trees contain the edge. So the fraction I will associate to the edge E, that's this blue one here, is 5/8. Okay, but you can do this for each of the edges. You get some vector, and the question I will ask is, what can you say about that vector? Okay, but a bit more general, I will think about the weighted case again. So here on top, I sum over all trees that contain E, and then I take the weight of the tree divided by the sum over all trees of their weight. So we go back to the example, and take, we care about edge 1 in particular. Then R1 of C will be C1, C2 plus C1, C3 divided by our original. Right, so every term here that contains the special edge. Is that definition clear? And if you want to forget about the weights, it's just counting number of trees that contain a specific edge. Okay. And well, so the name, I call this the relative resistance, and this is because of the fact that this is equal to the weight times the effective resistance of the edge. And again, this is some concept from electrical circuit theory. That's very rich, and in particular, it has this whole combinatorics of spanning trees contained in it. Again, this is something that you can compute quite easily. Like this looks like a horrible formula. This can be very big sums, but it turns out, and this is due to work from the 90s, that there exists a matrix. It's a projection matrix into the cut space of your graph, such that the diagonal of that matrix contains all the relative resistances of the edges. Okay, so this is an E by E matrix. Its diagonal is an E-length vector, and that vector is precisely the vector containing all the fractions that we care about. Okay. Then a second fact is that these numbers are not independent, as you might guess, right? They all live in the same graph, so it makes sense that these fractions are related to each other. And this is one relation that they always satisfy, which is called Foster's theorem, which says that if I sum all of these fractions together, I should get again this magic number and minus number of components. And if you want to prove this, it's quite nice to see it happening at least once. You just plug in this formula here, you switch the order of two summations, and you will find that this is just due to the fact that I have a homogeneous volume. So quite quick proof, or if you will, I know this is a projection matrix. This vector is its diagonal, so I take a trace of a projection matrix. I know I should get some dimension, so you just figure out what the dimension is of your graph, of your cut space. Okay, so these are the numbers I care about, and what is the question I will now ask and then answer is to find more of these relations that hold in. And I really want to find what is a full characterization of all possible such vectors that I get, right? So you pick a choice of edge weights on my graph, you compute these fractions for all the numbers, I get a vector that lives inside RE. I do this again and again and again, and I should get some subspace of RD. In particular, you have to align a certain hyperplane because this equality has to be satisfied, and so on and so on. What does that subspace look like? That's the question I'm posing now. Is the question a bit clear? Yeah.
Are your edge weights always positive?
Yeah, for instance, yeah. So indeed, so this would be a first thing we can say, right? Secondly, it's positive. Thirdly, it lies in 0, 1 because it's a fraction. And so there's a number of things exactly like. And what I first had done is to just try and enumerate some of these things, but it turns out there's like one nice way of getting all of them together. Will be the next slide. But yeah, it turns out that if you try to keep guessing, there's a lot of them that you should exponentially many equalities that hold for inequalities. Okay, so let's get to the characterization. It turns out a certain polytope will play an important role. So here I give a definition if you know this notation. So the spanning tree polytope of my graph G is the convex hull of indicator vectors of my spanning tree. So I'll give an example. So this is always, so for graph G, this is a polytope that lives in R to the E, so the number of edges. And what do I do? So I look at my spanning trees. So this graph has 3 spanning trees. To each of them, I can associate a 0, 1 vector. That's just the ones tell you which edges are present and the zeros which are not. This is a vector in R4. For each edge, it's just a binary choice. And then I take the convex hull, which is just everything that lies between these points. And I get a polytope, in this case, that lives in R4. That's called the spanning tree polytope. Okay. And now it turns out that the answer to the question I asked before is that the relative interior of this polytope, so everything but the boundaries and the vertices, that is a set of all vectors of relative resistances in your graph. So if I make a choice of edge weight C, I compute this vector of relative resistances, I will land inside my polytope. And conversely, if you give me a point from that polytope, it turns out there will be a unique choice of edge weights up to common rescaling, right? So everything times 4 or times 5. Such that the corresponding relative resistances will be my point I started from. Okay, so this is the bijective relation between us. This seems very surprising, at least for me it was, but it's actually just not hard to prove. It's a special case of something called the Atiyah-Guillemin-Sternberg convexity theorem. So this is something in symplectic geometry from the 80s, and then rediscovered later by matroids. People more interested in matroids. It's Gelfand, Goreski, Markford, and Saganova. And so once you know that framework and you make the right definitions, this just follows immediately from their results. In statistics, people know a similar result, which is called Birch's theorem. And it tells you that if you have over the collection of all distributions with a fixed marginal, that there's a unique one which maximizes the entropy, and that is a log linear distribution. And this implies also the result, at least in one direction above. So there's many different places where people discover and rediscover this. Then a second thing is that this bijection is very explicit and very nice to work with on a laptop, say, for fairly large graphs. So I mentioned before how you can compute R if you're given C, and you build this projection matrix and you look on the diagonal. I haven't given you the details, but it's not hard. And conversely, this is slightly harder. So if you're given a point in this polytope and you want to know the corresponding edge weights, there's a certain iterative algorithm, something like Sinkhorn algorithm, if you know that, in the theory of operator scaling, that it's not difficult to prove that it converges to the correct weights, but it was very difficult to prove that it converges efficiently, and this was only proven in the early 2000s. So it's work of Gurwitz and later Victorson and some other people. But this all works on a laptop for graphs up to 1,000 edges, for instance. So this is really explicit. You can really work with this quite easily. And then a second, and this is related to what Roy was, like what are some of the inequalities it holds? Well, these are all the inequalities. Okay, so if I have some vector R, and now I want to know, is this a vector of relative resistances in my graph, yes or no? Well, this is the case if and only if for each subset of edges, this inequality holds, right? So it says that the sum restricted to all elements in A should be positive or non-negative. And secondly, it's upper bounded by the number of vertices minus the number of components where you remove the complement of A. This is just, there are two numbers that you know it's bounded by, and this actually fully determines the polytope. Right? And so these are just the hyperplane inequalities of your polytope. Okay, and then it's known, you know, equality can hold if and only if certain things are true.
So wait, what does the notation there mean? The G minus E minus A?
So here I remove the complement of A. So basically I restrict my graph to the edges in A. So if I, you know, in this graph, if I would restrict to edge 1, it would be this graph.
Right.
Yeah. And then you now count number of components, so the components would be 2 here. So the thing on the right would be 3 minus 2 components is upper bounded by 1. So this just says that this edge has to be at most 1, which we knew already, but because it's a fraction. And so in this way, for every subset of edges you pick, you will get some inequalities that have to be satisfied. And when they do, we know that it's a valid vector. Yeah.
You said that all of these map to inside the polytope.
Yeah.
What happens when you go to the boundary?
So the boundary, there is a theory for the boundary coming from this whole symplectic geometry setting, and it would correspond to letting weights go to 0 or infinity. 0 is easy, infinity is a bit trickier, but it still actually works without a problem. But for my setting, I care about vertices, and the moment you start identifying things, you lose track of labelings of vertices, and that's why the boundaries are sort of, in my later results, they will be trickier. So that's why in this case, but yeah, the theorem is valid for the boundaries. And it's more trans like a diffeomorphism between two objects which contain the boundary as well. So yeah, good question. And that's yeah, partly also what happens here, like where the strictness comes from. Good question. Any other questions? I will move next to the application. Yeah. Okay. So now I'll describe an application to discrete curvature. So first, yeah, maybe one word about curvature if you're not so familiar with that. So curvature is some geometric theory of some geometric quantity associated to smooth objects like manifolds or surfaces. And it quantifies locally how your space is different from being like flat Euclidean space. Okay. So here I give 3 examples, prototypical examples of positive, 0, and negative curvature. And one sort of illustrative definition is to think about the growth of geodesic balls. So you pick a point at your surface that you care about the curvature, and you look at the growth of geodesic balls. So how fast does the volume of these balls grow? And you compare that to Euclidean space. If it grows quicker, you call it negatively curved space. If it grows slower, you call it positively curved space. And the rate at which it's quicker or faster tells you also the magnitude of the curvature. So that's an example of how you could define the scalar curvature around the point. Now, in discrete curvature, we try to think in similar terms about discrete objects such as graphs. You could, for instance, think about, okay, I take a vertex here and I look at the growth or how many vertices are there in the ball around the point and compare that between these 3 spaces, then you should get roughly that this is positive, 0, and negative. Okay, but how do you make precise definitions? And that's for a large part what discrete curvature is about so now, because it's sort of developing theory. But it turns out that you can do this actually quite well, right? You can start from a definition on the continuous side, you sort of relax it until it also works for discrete objects, things like finite metric spaces. And then you just declare that's now a curvature on your graph, and you go with that. And it turns out that this often works. You don't just get the definition, but you also get along a lot of the theoretical results. Differential geometries is a very well-developed field. There's a lot of strong results, and many of those can actually then be translated also to things in graphs. And I'll give some examples later of the types of results we get in that setting. There's many different ways you can do this. And so people have done various approaches to this. So using optimal transportation, Laplacian operators, entropy functionals, and then in my own work, potential theory. And well, I'll give you sort of the gist of how you get to curvature from potential theory. And so again, potential theory is sort of the study of electrical optimal measurements, you could think. So let's imagine the following experiment. So we have some conducting body, say some metal object, to which we introduce some charged particles. So that's these pluses here. So maybe you rub it against your shirt or something, and now it's a charged object. Then you may know from some physics class that if these particles have the same sign, they will repel each other because that reduces the energy of these particles or of the system. And they will do so in such a way that minimizes the total energy, resulting in what is called an equilibrium configuration. And in fact, it will turn out that the charges will be distributed on the boundary of your object in such a way that it will be concentrated on points with higher curvature and less dense in points with low curvature. So that's sort of a physical fact again that we know from potential theory. And so this is then an inspiration to try and do the same thing on graphs. So what we have here is we say, okay, we have some distribution or a density of charge on an object, and we can associate that a certain energy, like how close are things on average. We want to minimize that. That's a variational problem. If we solve it, we get something that sees curvature. So we do the same thing on graphs. We say, okay, what if I have some distribution on the vertices of my graph? So just think of a number between 0 and 1, or maybe something that sums to 1 to be normalized. And then I can associate to that some energy functional, which measures how things are, close are things on average. And we know this wants to be minimized, so we can formulate a variational problem. Turns out this has a unique solution, which we then call well, the resistance curvature. Okay, so we say this is now a scalar curvature on a graph, following this intuition from the continuous setting. Okay, so that's what I did with Renault in 2022, and then later had a follow-up with Stefan, who independently also had an approach where they used a different type of energy functional based on well, the normal distance, whereas we used resistance distance to define this energy functional. And so what I show here are some first experiments you can run. Okay, so what I show here is this value of the density. Okay, and what we really want to reproduce in this example. So here I take a Euclidean disk, so just unit disk in the Euclidean plane, which we know should have zero curvature, at least away from the boundary. So what I do is I sprinkle some points, and I make a graph out of those. Like if vertices are close by enough, I connect them. Then I do this whole variational problem that I mentioned before. I compute the curvature, and we find indeed that sort of on average we find zero curvature in the bulk. So this sort of gets what we hope. Then these three examples are sort of very cartoon pictures of the three examples I gave here, right? Something where you would hope constant positive curvature, where you hope zero curvature on a path graph, and negative or non-positive curvature in theory of a tree. And this works well. So if you compute this resistance curvature, you get what you hope. Okay, so these are some first sanity checks. And then there's a lot of other arguments you need to make and things to prove to qualify it as a curvature. Okay, so I haven't given a definition yet of the curvature. And the reason is because it turns out there's a very simple formula for it in terms of the combinatorics of your graph, again, based on spanning trees. So you don't really need to solve this variational problem. You can just do some counting. And it turns out that this formula is true. So the resistance curvature at the vertex V is equal to 1 minus half the expected number of neighbors in a random spanning tree. Okay, so let's look at an example here. So say we want to know the resistance curvature of this vertex in red here. So we take 1 minus half, then we compute the average number of neighbors of this vertex. It turns out this is 1/8. Okay, so here this is a definition, but this is equivalent to the whole procedure I described in the last slide. So this is the resistance curvature at a vertex. Okay. So as in the rest of my talk, so here I just think about uniformly distributed random spanning trees, but you can also say, okay, if I have a choice of weight, it makes sense to reweight my trees using the weights of a tree, right? So if now a tree contains a lot of edges with high weights, it will have a higher probability and will count more in this computation. Okay, and if you do that, then you can actually find the resistance curvature based on your relative resistances, and some simply saying 1 minus half the sum over all edges that contain your vertex V of the relative resistance. Okay, so here we are back with the relative resistance. Is that definition a bit clearer?
Are there similar formulas, similarly convenient formulas for different definitions of your energy?
So the only really similar one would be Steiner curvature, which I don't think allows for this. So this is really, again, because we work with effective resistances, which is this whole Laplacian theory behind it. So it's very particular to that setting. Yeah. But it's, yeah, I mean, but this formula actually quite looks like other notions of discrete curvature, something called Forman-Ritchie curvature has a formula very similar to this, but with a different choice of weight that you can actually specify yourself. So this is one of the arguments that we use in our paper as well to argue. This is very closely related to other notions of curvature. But so here, yeah, this sort of follows from this other procedure. Yeah. Okay, so here we have again some curvature for each choice of okay. So why do we care about curvature? As I mentioned before, there's a lot of nice theoretical results we can port from the continuous setting. And in particular, what people care about in differential geometry spaces with non-negative or positive curvature. So it makes sense to try and do the same thing for graphs. I'll give you a few results here. First, some examples to keep in mind. So vertex transitive graphs, highly symmetric graphs, they all have constant positive curvature. So things like cycles, cliques, or hypercubes, just to have some examples in mind. Then there are some operations to which you can do in the graph that's sort of this property behaves well. One of them is called Cron reduction. So again, just a sketch of what this means. So I take some labeled set of vertices in my graph, I remove it, so G minus U means this graph here, and then I add a clique, so all possible edges between neighbors of my graph, that's this graph here. And then it's true that the set of graphs which have non-negative resistance curvature is closed under this operation. So once you have some examples, you can construct many more using this simple operation. And this is some typical geometric results that you get from these curvature theories, which I was together with Andrea and Stefan. And so what we showed is that if a graph has curvature lower bound by some positive constant k, then we get bounds on the spectral gap as a function of k and bounds on the diameter of our graph also as a function of 1 over square root of k. So these are typical results in differential geometry. So it would not be a surprise if G here gets turned into a manifold and you expect many similar things, maybe with different constants, but this is the type of things we try to find often in discrete curvature as well. Then something that's much more really graph theoretic, some connectivity statement. This is due to Fiedler in 2011. And he showed in a very different context, so this was simplex geometry, but it turns out to be equivalent, that if your graph is connected and has positive resistance curvature, then it is also one toph. So this is a connectivity statement that tells you if I remove k vertices from my graph, I get at most k components. So these are graphs that are hard to destroy into many small pieces. If you want to have k pieces, you need to remove k vertices. Okay. And so this actually is a result that caught my attention for the following reason, that the first statement really depends on the choice of edge weights. I've given you a definition of resistance curvature for edge weights, whereas the second statement only depends on the combinatorics of just the vertices and the edges, and it doesn't see the edge weights. So if you choose badly your choice of edge weights, you might miss the fact that it's positively curved, and you might not realize that this is implied. Okay, so that was there's sort of a tension here between two different levels at which these objects and properties are defined. And that's what I will try to, I answered, was the following question, or that motivated this question, which is as follows. So the question is, which graphs G admit a choice of weight C such that the resistance curvature is non-negative? And well, we know it cannot be all of them, because we know this is quite a special class of graphs. So it cannot be all of them, but which graphs are they? That's the question I really have. Okay, it turns out the answer is again related to some polytope. In this case, the matching polytope of a graph. So first, what is a matching in a graph? So a matching is a subset of edges. So I'll write M here, such that every vertex is touched by at most one of the edges. And you can see here, there's no vertex here that sort of touches two of the edges. Again, to this object, you can define polytope. So matching polytope is again lives in R to the E, and it's defined in the very same way, right? For each of these, you can define a 0, 1 vector that lives in RE. You take their convex hull, and that's the matching polytope of your graph. Okay. Well, we will actually care about twice dilated matching polytope. It just means instead of a 0, 1 vector, I'll take a 0, 2 vector. I just blow it up by a factor of 2. And then the result is as follows. So the answer to my question is a graph G admits weights with non-negative resistance curvature if and only if the interior of my spanning tree polytope intersects the twice dilated matching polytope. So these two polytopes are purely defined based on your graph. You can intersect them and see if there's intersections on empty. If it's the case, then we know I have some weights with non-negative resistance curvature. And in fact, this intersection is in bijection with those weights for which you get non-negative resistance curvature. Okay, but let me just illustrate again to make this a bit more tangible. So say we want to know this graph that I drew on the boards, if it has non-negative resistance curvature.
Enable /2.
And we forget that it's vertex transitive, so we already know it's positively curved. So first of all, we look at the matchings. So there's, okay, I forgot there's also the empty matching here, but then 3 matchings of one edge, these 3. We look at the corresponding polytope. So this will be vector 2, 0, 0, that's that point, 0, 0, 2, that's that point, and so on. We take the convex hull, that's this tetrahedron here. So think of it, this contains the origin as well. Then we look at the spanning tree polytope. There's 3 spanning trees. So this is the point 1, 1, 0, that's that vertex. 1, 1, 0, that's that vertex, and so on. So we have, again, the triangle in R3 in this case. And if I intersect them, I see that the intersection with the interior of E of G is non-empty. So this certifies that my graph admits weights with non-negative resistance curvature. And in fact, in this case, it shows that any choice of weights gives you non-negative resistance curvature. And then well, you can show that this only works for cycles. Okay, is there any question about that result?
Is there any intuition as to what are the matches doing here?
Yes, there is. Yeah. So, so the reason matching show up is if you go back a few slides. So, what am I asking when I ask that this is non-negative? And I'm saying that the sum at every edge, at every vertex of all the incoming edges at the relative resistances, sum up to at most 2. And this sum should be at most 2, and then this thing is non-negative. And this inequality of something summing up to at most 2 is precisely one of the hyperplane inequalities of the twice dilated matching polytope, right? Because the matching is defined fundamentally by saying by inequalities at vertices that things around it cannot be, it can be at most 1. And if you relax that, so you take the linear program that relaxes it, then you get these inequalities, and it turns, so then you know that it's satisfied, but then it turns out that all other inequalities that cut out the matching polytope are implied by the interior of the spanning tree. That's more surprising, but it's true. And so that's also why the number 2 appears, because the number 2 appears here. Yeah.
Is there a connection to the permanent of the adjacency matrix? Because whenever I see counting and matching, I think of the permanent.
Not immediately that I know at least. So one thing you could say is, for instance, in the case of planar graphs, there you have this counting form, like this permanent becomes a determinant, or like there's a determinantal formula for counting matchings.
Yeah.
And then you actually have, so then you could say that a point in this interior appears in two ways. It's, first of all, you can see that it's coming from sort of a marginalization operation on distributions on spanning trees. And at the same time, it's also the marginal coming from a distribution on matchings, both of which come from determinants. And so, I mean, I don't have an answer to what is the relation, but that's the direction that I'm interested in, for instance. Yeah. Okay. And in other cases, it would be between a determinant and a permanent, but that's, I would say, more tricky somehow. But yeah, so to me, this is curious that you can get both from spanning tree distributions and matching distributions, both of which are determinantal point processes as well. So a lot of structure that there you can both get the same marginals. That's actually, well, the fact that that works is part of this theorem as well. Yeah.
Okay.
Yeah. And this was also the last slide. So if there's no questions, then thank you.
Great, thanks, Karel. We just had a bunch of questions, but if there are any more, and also people online, if anybody has a question, feel free to raise your hand or say something in the chat. Seeing anything online? So I think we answered all the questions along the way. So yeah, let's thank Karel again.
Yeah, and so it's online for a few weeks now, the paper associated.
Ciao, Nico.
Just really wanted to say hi. Ciao, everyone.
Nico, no?
Thanks for Nico. I don't know if you can see it, but he was waving.
So, it's busy now?
Yeah,
So that you know each other.
Yes.
Good.
The one next door, I think. You're next door.
Start with this partition function codes for an energy.
Yes.
For. And maybe define the especially way from this.